Here we are again with question number 5. How to attempt this? Just run through the question. Greedy goblin grip hook, let's call him some person G, name hardly matters, has a regular 2000 sided polygon whose each vertex has a single coin. In a move, he chooses a vertex, remove one coin from each of the two adjacent vertices and adds one coin in the chosen vertex. So he basically removes two and adds one. So he keeps the remaining coin for himself. He can make such a move only if both the adjacent vertices have at least one coin. So if one of the vertex doesn't have a coin, the move at that particular vertex doesn't proceed. Grip hook stops only when he cannot make any further move. What is the maximum number of coins and minimum number of coins he has collected? Remember, it's about the number of coins collected and not the number of coins on the polygon. So for better understanding, what I do is I consider a polygon inscribed in this circle, and let me take two diagrams, one for maximum and one for minimum, whenever the case comes like that, and try to understand so that we relate this thing. Let the vertices be A1, A2, A3, A4, A5 up to so on A2000, A1999. Now, each vertex initially has one coin. To understand better, I start with one operation at any position. So let's do it at A1, A2, A3. Both these become 0 and this becomes 2. Try to understand. The remaining all are still 1, 1, 1, 1. If we want to take out maximum number of coins, we would appreciate if there was a possibility of taking out all the 2000 coins. Practically not possible, because to remove a coin you need at least 3 there, so that adjacent. 1999 is also not possible, that's quite understable. But had it been that there is a possibility that 1998 coins can be withdrawn, but obviously this can be the maximum one. For 1998, what we do is just try and get the trivial solution. Now I work on these 3. Now remember, it says that it can make a move if both the adjacent vertices have a coin. So the particular vertex may not have a coin, still one goes in this, one goes in this, removed out of this, and this becomes 1, 1, 0. One removed, and from that one has put here, rest all again remain to be 1, 1, here it was 0, 1, like this. Now I cannot play further on this 1, 1, 0 because adjacent one of the, but I can definitely play on this 1, 0, 1. So I leave this one of A2 here. Now 1, 0, 1 will become, these two will get inside 0, 1, 0, and the other one once I leave this here, and this continues. The next 1, 0, 1 will become 1, 0, 1, 1, 0, 1, 1, 0, 1. And if you can relate this way, I am doing it on a circle, you can do it linear and then relate it with the last one. You realize that at the end only 2 coins remain there. So for the maximum, the answer is 1998. How to represent this in the language? All you need to do a recursive relation or a kind of successive working, that for every AK plus 1, AK plus 2, 1, 1, 0 with 1 becomes 0, 1, 0, and every 1, 0, 1 moves to the next slide, next slide, next slide, and so on, and hence it reaches to a situation where all the 1998 coins are removed. Nothing more than this is possible, because you obviously cannot remove 1999 and 2000 coins. Coming back to the situation when we want a minimum. Once again we mark the vertices. And so on. Initially, all with 1 coins. What we have to understand is, if we want to withdraw minimum coins, that means the number of coins on that polygon should have been maximum. And after any particular set of operations, say for example I operate here, so I am left with 0, 2, 0. Now this particular value 2 cannot become 3, whatever be the case, because you will never have an adjacent working come here. Even if I write it as 1, 1, either this 2 will become 1 or this 1 will not become 2 for whatever be the case. So the maximum coin on a particular vertex cannot go beyond 2. So our aim should be to make as many 2's possible. That means place as many as pair of coins on a vertex, and that you can do with every 3 successive. So another 2, another 2. So at a set of 3 you get maximum 2. So there are 2000 vertices. I can think of this situation that there would be 2000 by 3 the greatest integer triplets, which essentially is 666. Am I right? But each triplet has 2 coins, so the number of coins on the board is, and of course this cannot go beyond this because we have optimized the number of 2's. You cannot get a single 3 there. So the minimum coin that could have been withdrawn is 2000 minus this, which is 668. The challenge of course would have been the understanding to be represented in the language of mathematics properly with proper terms.